In this video, I wanted to discuss the definition of a binary search tree and a few examples and non-examples of binary search trees. So recall that a binary tree is a rooted tree where each node or vertex can have at most two children, a left child and a right child. So any vertex can have at most two children, a left child and a right child, and each specified child can be present or absent. So on the top, both of these children are present, but if we look at, say, this node, let's say that's called Z, then Z has a left child but does not have a right child, and that is okay. Now, a binary search tree is a binary tree, so it's rooted, and again, the root is drawn up at the top. It's rooted with values at each node or each vertex that satisfy the subtree conditions. And the subtree conditions are that if X is the value of a node and Y is the value of it in its left subtree, then X must be greater than or equal to Y. So if this is the node X, then every node in the left subtree, so this entire piece is the left subtree of X, everything there must be, any node Y in there must be less than or equal to X, and any nodes in its right subtree must be greater than or equal to X. So everything over here, in this case, the entire right subtree is just that single vertex, but everything in that right subtree has got to be greater than or equal to X. So given the definition above, the binary tree that we see here is not a binary search tree. So why don't you pause and take a moment to find all errors. So what are all the reasons that this is not a binary search tree? So pause and try to think about that for a moment. Okay, so let's see. Why is this not a binary search tree? Well, first of all, here is this value 16, and 16 is in the left subtree of 15. So 16 is in left subtree of 15, but is greater than 15. So that is one error. Another error is here. 13 is in the right subtree of 15, but 13 is less than 15, so it should not be in its right subtree. And finally, this value 27 is in the left subtree of 25. So this is in the left subtree of 25, but it is greater than 25, so that should not occur. You might have wondered if this is okay, that the value 8 is repeated, and this is okay. So those two values of 8, it doesn't matter in which order they are. They are following the criteria that this value in the left subtree is less than or equal to the value at the node. This number 8, therefore, could have also been in the right subtree, and that would have been okay. All right, so noticing this, this actually tells us that binary search trees have a special property, that if you have n nodes and n distinct values, there is only one way to place those n distinct values in those nodes that will meet the criteria of being a binary search tree, that subtree criteria. And remember that distinct in math means different from each other, so the values 8 and 8 were not distinct from each other above. So knowing that, try to label the binary search tree below with those values listed below. So give that a shot and we'll talk about it in a moment. Okay, let's label the nodes of this binary search tree. So first of all, we see that in the left subtree of the root node, we see that there are 5 nodes or 5 vertices over here. So the first 5 values, 1, 2, 3, 4, 5, must all go in that left subtree. And that tells us that the root node is going to be the value 22. So 22 is going to be the root node. Now we can sort of look at each of those subtrees individually. So we see that in now, let's switch colors. Now this right subtree has only one value, whereas the left subtree has 3 values. So the first 3 values must go in that left subtree, and the only value larger must go in the right subtree. So this must be 20, this must be 10. And we have 1, 5, and 9 to put in still. So 5 has to be the value that's greater than 1 value and less than 1 remaining value. And now if we switch colors again, we can look at the right subtree. So we have these 4 values left to put in. We see that all the values are in the left subtree of this node. So all remaining values are in the left subtree of this node. So this must be greater than everything remaining. So this must be the value 42. And now the next node has a value less than it and a value greater than it. So this must be the node 30, this must be 25, and this must be 40.